Hello my friends, welcome to a little discussion on how to solve problems involving calorimetry. So today we're going to talk about how to find the specific heat of an object using a water calorimeter. We'll also talk about how to then use algebra to find weird things like the starting temperature of something using calorimetry. And basically it's just a use of algebra at that point. Let's get started. So the first problem we're going to take a look at is this one. And we've taken a 5.51 gram sample of copper, and we've heated to 99.8 degrees Celsius, dropped it into a calorimeter with 15 mils of water, and the temperature of the water increased from 22.6 degrees to 25.3. And what we want to know is what's the specific heat of copper. So if right now you're like, I think I know how to do this problem, go ahead and hit pause and try and work through the problem. Otherwise, I'm going to actually talk through the solution, and then I'm going to give you another chance to pause, and then I'm going to actually work through it. So here it goes. In this problem, I notice a few things. I notice right away that I've got three temperatures. I've got the beginning temperature of the metal, I've got the beginning temperature of the water, and I have the ending temperature of the water. But then I think, oh yeah, wait a second. What makes this metal stop cooling off is because it reaches the same temperature of the water. So this ending temperature here is both of the water and of the metal. I also noticed that I have the starting masses of the water, because I know 1 gram per milliliter would give me the mass, and the starting mass of the copper. I also have this number in my head of C of water is equal to 4.18 joules per gram degree Celsius. So I have that for the water as well. So yeah, I'm ready to go. So what I'm going to do here is, we notice the water is heated up. We can actually use the amount of heat up, the amount of temperature change here, and the specific heat of water and the mass of water to find how much heat the water absorbed. And we know that heat must have come from the metal. So then we can use that heat to figure out the specific heat of the metal. So at this point you're like, I think that makes sense to me. Go ahead and hit pause and work it out yourself and see if you can get it. If not, let's do it. Here it goes. So this is the heat the H2O, the water, gains. To find that number, we go Q is equal to MC delta T, and this is for the water. So everything here is going to be water-based. So I'm going to say Q is equal to the mass of the water, which is equal to 15.0 grams, because the density is 1 gram per milliliter. The C of water is 4.18 joules per gram degree Celsius, and that's going to be equal, or times, the change in temperature, which is the ending temperature, 25.3 degrees Celsius, minus the beginning, 22.6 degrees Celsius. And when we do that, we get a Q value for the water of 169.29 joules of heat. Now that's a positive number because the water is absorbing heat. Now this is for the water. I'm going to put H2O here. Now for the metal, the Q of the metal is actually equal to the opposite of this, because if the water gained, the metal must have lost. So it's negative 169.29 joules, and that's for the copper chunk of metal. Okay. So the same amount of energy, but in the opposite, the heat's going in the opposite direction. Here it's going into the water, here it's going out of the metal. All right. So the next thing we need to do then is we need to figure out, we know how much heat the copper absorbed. We need to figure out the C, the specific heat of the copper. We know that Q is equal to MC delta T, and all these are copper things, right? So I'm going to use only copper numbers here. And I want to find out C, so all I'll do is divide here by M and delta T. And if I divide this side by M and delta T, I have to divide this side by M and delta T. So M and M cancel, delta T and delta T cancel, leaving C is equal to the heat given off by the metal divided by the mass of the metal and the change in temperature of the metal. So I'm going to plug some numbers in here. So I've got my Q over here, my heat over here. So I have negative 169.29 joules and it's negative because the metal is losing heat, divided by the mass of the metal, which is 5.51 grams, and the change in temperature of the metal, which it went from 98 to 25.3. So we do the final minus the initial. So it's 25.3 degrees Celsius minus 99.8 degrees Celsius. Now you may notice that this is going to give us a negative change in temperature, which makes sense because we lost temperature, so there should be a negative change. And here we get a C is equal to a whopping 0.412 joules per gram degree Celsius. Bam. That's it. So basically what we did is we found the heat water gained, we attributed that heat coming from the copper, and then we just solved for C here algebraically. All right, best of luck to you. Let's do the next one. Now this problem involves using some algebra and some creative thinking to find just some weird thing like a starting temperature. My guess is that you would probably want to measure the temperature of a starting liquid with a thermometer rather than using calorimetry to do it, but it's possible. So here we're going to use aluminum, and we know aluminum's specific heat. This is an important number to know in this problem. We know the mass of the aluminum, and we know the mass of water. We know the starting temperature of the water and the ending temperature of the water. We don't know the starting temperature. But just by looking at these numbers, I can see the water heated up. So that means the aluminum must have cooled down. So the aluminum is going to be some higher temperature here. So it's going to go from hot to cold because the water went from cool to warm. All right. So this kind of starts in the same way. We need to first look at what the change in heat is of the water. Because we also know, actually, let me write that down real quick. The C of the water, the specific heat of the water, is 4.18 joules per gram degree Celsius. We'll need that as well. So we're going to first find out the heat the water gained. We're going to then use the specific heat of aluminum and the mass of aluminum to then find the change in temperature that the aluminum went through to give off that much heat. And then we're going to back out the starting temperature of the aluminum. All right, so if that made sense to you and you're like, okay, I'm good, go ahead and work through the problem on your own and check your answer by just zooming ahead on the video. Otherwise, let's do this thing. So first we need to do how much heat the water gained. So just like before, heat water gained. And that's going to be Q equals MC delta T. All these numbers here are going to be water numbers, right? So we're not going to mix the numbers at all. If we're finding the heat of the water, we're going to keep them all the same into the water. So the heat the water gained is the mass of the water, which is 50.0 grams. And I know that because it's 1 gram per milliliter, times the 4.18 joules per gram degree Celsius, times the change in temperature. So I'm going to use the final temperature, 28.1 degrees Celsius minus 21.5 degrees Celsius. And when I do this work, I'm going to get that the Q is equal to 1,379.4 joules. And that's the Q of the water. Of course, the water absorbed energy. That means the metal must have given it off. So Q of the metal is equal to negative 1,379.4 joules. And that's for the metal. And here I'm holding off rounding yet. I'm going to round at the end. I'm going to retain some significant figures until then. All right, so now that I know how much energy the metal lost, it lost this much energy, I can use that, my specific heat, and the mass to find the change in temperature. So this here is the change in temperature of metal. So to give off this much heat, I'd have to have this change in temperature. So Q is equal to MC delta T. This is all aluminum stuff, so I'm going to use only aluminum numbers here. So I need to find the change in temperature, so I'm just going to divide both sides by M and C. M and C, mass and mass cancel, C and C cancel. So I get that the change in temperature of the water is equal to QMC. So to make this much heat, I've got to have this big of a temperature change. Let's plug some numbers in. So I get negative 1,379.4 joules divided by the mass of the aluminum, which is 32.6 grams, divided by C of aluminum, which is 0.900 joules per gram degree Celsius. Now I'll tell you, one of the big problems people have with these problems is they mix stuff. So they'll use some water, some aluminum stuff. Be really disciplined. When you're talking about the metal, you only use numbers about the metal. When you're talking about the water, you only use water numbers. Yeah? And the only number that crosses over between them is the final temperatures. They'll be the same between both objects because they'll cool off together. And then also the heats will be similar. So one will be positive, the other will be negative. So those two things will help you go between them. So when we do this work, we get a change in temperature here of negative 47 degrees Celsius. And at first you might say, oh my gosh, that sounds crazy. A negative temperature, it can't be cold. This is a change in temperature, which means the temperature of the metal decreased by 47 degrees. So really what we're looking for is a temperature that's 47 degrees hotter than where it ended up. So what I can do here is just say, okay, so that means my final temperature must be 47 degrees more than my ending temperature. I can do 28.1 degrees Celsius plus 47, oops, this should be 47.0. 47.0 degrees Celsius, and that's going to give me a final temperature of 75.1 degrees Celsius. Bam. Now if you're like, hey, you know what, I prefer math equations, not this reasoning stuff, we could do it this way as well. We could say our change in temperature is equal to negative 47.0 degrees Celsius. And we know that change in temperature is always the final minus the initial. So we can say, hey, this is equal to the final temperature minus the initial temperature. So F for final, I for initial, is equal to our change in temperature, which is negative 47.0 degrees Celsius. And then to solve for I here, Ti, I would add the initial temperature to both sides and then add 47 to both sides. So I would get here T initial is equal to the T final plus 47.0 degrees Celsius, and that is just what I did there. I'd get the same 75.1 degrees Celsius. So it works great either way. You can either reason through it using logic and understand what the numbers mean, or you can apply these math formulas as well. I would actually prefer if you stuck down here in this route, right here, because when you do that, you really show that you understand what's going on and not just how to work equations. All right, my friends, it looks like